Hello, this is Matt Dean with A Plus College Ready, and today we're going to look at some uniform circular motion practice problems. So practice problem 1 says, what is the maximum speed at which a car can safely travel around a curve if the radius of the curve is 100 meters and the coefficient of friction between the tires and the road is 0.2? Well, in this case, what you've got to know is that the frictional force is actually acting toward the center of the circle. So if we drew a free body diagram for this car, we would have weight acting down. Assuming we're on flat ground, we have a normal force acting straight up. Those two cancel out. The frictional force is acting toward the curve. So that frictional force is a net force. It's also a centripetal force. So to work this problem, we're going to set the frictional force equal to the centripetal force. We know that the frictional force is equal to the coefficient of friction, mu, times the normal force. And we know that the centripetal force is equal to m v squared times r. mv squared over r, rather. So since we're on flat ground, we also can assume that the normal force is equal to the weight. So let's make a substitution. We'll substitute mg for normal force for weight, set that equal to mv squared over r. You can see that the masses cancel out. And in this case, we're trying to solve for velocity. So if we solve this out for velocity, we end up with v equals the square root of r times mu times g. And if we substitute in our numbers here, we end up with r is the radius of curvature, so that's 100. Mu is 0.2, and we'll use a g of 10. We end up with a velocity, once we take the square root of the whole quantity, of about 14.1 meters per second. All right, so here's practice problem 2. If the distance between two objects is increased by a factor of 8, while the mass of each object is increased by a factor of 4, how is the force of gravity between the two objects affected? Give a numerical answer. Well, first of all, we need to think about Newton's law of universal gravitation. And this is what it looks like. G is the gravitation constant, so that's always the same. If we say this is the original force, what we're doing in the new problem is G doesn't change. We're increasing M1 by a factor of 4. We're increasing M2 by a factor of 4. We're increasing the distance between the two objects by a factor of 8. Well, that has to be squared, so we've got to have 8 squared here on the bottom. So that becomes 64. So you can see that we've got 4 times 4 on top, 16. We've got 64 on the bottom. That reduces down to 1/4. So what that tells me is that the new force, after doing the increases in mass and distance, the new gravitational force is 1/4 of the original force. All right, so here's number 3. A satellite of mass 5.5 times 10 to the 5th kilograms orbits the Earth. We're given the mass of the Earth at an orbital distance of 6 times 10 to the 6 meters. If the satellite must maintain a constant distance from the Earth, what is the satellite's orbital velocity in terms of meters per second? And also, what's the period? So what we've got to remember here is that it's the centripetal force that's keeping the satellite in orbit. And that centripetal force is the gravitational force between the satellite and the Earth. So we're going to say centripetal force is equal to gravitational force. Remember that centripetal force is mv squared over r. And that's equal to the gravitational force, which is g, m. In this case, this m over here on the left, this is the mass of the satellite. So I'm going to say mass of the satellite times the mass of the Earth over r squared. So what you can see is that this right here is the mass of the satellite. Those are going to cancel out. So if we continue to solve this for v, we'll multiply both sides by r. This r is going to cancel with one of those. We're going to take the square root of both sides. And that's what we get when we solve it out. So we're going to substitute in G, 6.67 times 10 to the negative 11th. We're going to substitute in the mass of the Earth, 5.97 times 10 to the 24th kilograms. And we're going to substitute in the orbital distance, 6 times 10 to the 6 meters. We'll take the square root of that whole quantity and end up with a velocity of 8.15 times 10 to the third. And that's in meters per second. So that satellite is moving really, really fast. So next we want to find the period. And what we know about the period, an equation that will help us with this is that the velocity of something going in circular motion is equal to 2 pi r over the period. So if we solve that for the period is going to equal 2 pi r over v. Well, in this case, r is that orbital distance. So we're going to end up with 2 pi times 6 times 10 to the 6th meters. And all that's going to be divided by this velocity right here, 8.15 times 10 to the third meters per second. And when we do the math, we end up with a period of 4.62 times 10 to the third seconds. And remember, that's the time it takes for one complete orbit. All right, here's practice problem 4. A planet has 3 times the mass of Earth and 5 times Earth's radius. The magnitude of the gravitational field near the planet's surface is. What we want to realize here is that the weight of an object is caused by the force of gravity. Remember that weight is mg, and it's the mass of the object. In this case, I'm going to put mass of object times g. And the force of gravity is the gravitational constant times the mass of the object times the mass of the Earth all over r squared. So what you can see is the mass of the object here is going to cancel out. And that the g, in this case, this is the strength of the gravitational field, is equal to the universal gravitation constant times the mass of the Earth over r squared. Now in this case, we don't need to plug in g or me because we're looking for this in terms of comparison to Earth. All we really need to look at is this r. And what we can see is if we plug the radius in this new planet is 5 times Earth's radius, so we square that. And so they're going to have 25 here on the bottom, 5 squared. The mass of the new planet is 3 times that of Earth. So this is going to be 3 times me. So essentially what's that's telling us is that the new planet is, its gravitational field is going to be 3/25 of Earth's. Remember that Earth is 10. So it's going to be 30 over 25, which is going to reduce down to 6/5, and that's measured in newtons per kilogram. So again, the strength of Earth's gravitational field is newtons, 10 newtons per kilogram. So our answer here is B, 6/5 newtons per kilogram. All right, here's practice problem 5. 2 pieces of space junk of equal masses are in circular orbits around the Earth. Object A has a speed of v. The orbital radius of object B is 16 times that of object A. What is the speed of object B? Well, what we've got to remember to work this problem out is an equation we derived in problem 2 or 3 earlier. Remember, it's the force of gravity that's acting like a centripetal force. It keeps objects in orbit. Remember that the force of gravity is g times the mass of the object times the mass of the planet, we'll say in this case. In this case, it's the mass of Earth over r squared. Centripetal force is the mass of the object times its velocity squared over r. So what we can see, again, mass of object cancels. If we solve this out for, in this case, v, multiply both sides by r. That cancels one of these here on the bottom. So we end up with v equals the square root of g me over r. So we're seeing that the orbital radius of B is 16 times that of A. But what that's going to tell us is that the speed is going to end up being about the square root of 1 over 16, because it's going to be 16 right here. So the square root of the radius, the speed of object B is going to be equal to the square root of 1 over 16 of the speed of object A. So that's going to end up being V equals 1/4 of the speed of object A. Which means in this case, our answer is D. All right, so here's practice problem 6. A satellite orbits a planet in circular orbit. The mass of the satellite and the distance between the center of the satellite and the center of the planet are known. What additional information is needed to calculate the speed of the satellite? So just like we saw in practice problem 5, we derived this equation for the speed of a satellite, in this case going around Earth. And the problem tells us that we know the mass of the satellite. We really don't need to know that. We know the distance between the center of the satellite and the center of the planet. That's what R is. We know the universal gravitation constant. So the only other thing that we need to know to find the velocity of that satellite is the mass of Earth, or the mass of the planet. In this case, we're assuming it's Earth. So our answer is going to be C. All right, so here's practice problem 7. So a person who weighs 1,250 newtons on Earth travels to another planet that has 3 times the mass of Earth and 4 times the radius of Earth. What's the person's weight on the other planet? Well, what we've got to realize is that the weight is caused by the force of gravity. So the weight is going to change, but the weight is made up of mg. The force of gravity is universal gravitation constant. In this case, times the mass of, we'll say, the person, times the mass of the planet over r squared. Okay. So in this case, we're going to assume that the mass of the person doesn't change. Big G doesn't change. But what does change is the mass of the planet. The mass of the planet is 3 times that of the mass of Earth, and the radius is 4 times that of Earth. So this becomes 4, and that 4 gets squared. So that's telling you that the new mass is going to be 3 on top over 16 on the bottom. 3/16 of the original weight. And if we take 3/16 of 1,250, we end up with about 234 newtons as the weight of the person on the new planet. All right, so here's practice problem 8. So we've got a ball that's being whirled in a horizontal circle. The ball undergoes uniform circular motion. Which of the following best illustrates the direction of the velocity when it reaches point X? Well, here's point X down here. So the ball's going around the circle like this. So it gets to point X, still going in this direction. What you've got to know is that in uniform circular motion, the velocity of the object is always perpendicular to the radius, to the direction the force is coming from. So the force is coming from here, from this string. The force is pointing always toward the center. The velocity is going to act perpendicular to that force at that instant in time. So our answer here is going to be C. All right, so practice problem 9 is a continuation of problem 8. In this case, we want to know what's the direction of the net force acting on the ball at point X. Again, the ball's moving this way, counterclockwise. When it gets to this point, what's the net force? What you've got to remember is that in uniform circular motion, the net force is the centripetal force. And the centripetal force is always acting toward the center of the circle. So our answer here is going to be A. All right, practice problem 10 is also a continuation of 8 and 9. In this case, we want to know what's the direction of the acceleration of the ball at point X. So again, the ball's going in a counterclockwise motion when it gets here at point X. Remember, the net force is the centripetal force. It's pointing toward the center of the circle. Anytime an object is moving in uniform circular motion, it's always going to be accelerating toward the center of the circle, toward the direction of the centripetal force, which is the net force. So in this case, A is our answer. All right, here's our last practice problem. Practice problem 11. 2 bags contain an equal number of identical masses. The 2 bags are separated by a distance of r. 1/3 of the masses from one bag are moved into the other bag. If the magnitude of the original gravitational force between the 2 bags was F, what is the magnitude of the gravitational force after the masses are transferred? So when we started off, the gravitational force was something like this. But what we do now, let's say we took 1/3 of the masses from M1 and we moved them over to M2. What that means is that the mass of M1 now is going to be 2/3 of what it originally was. And the mass of M2 gained an extra third. So it's now 4/3 of what it originally was. R didn't change. So all that changed was the distribution of the masses. So if we multiply those fractions on top, we end up with 8/9. And what that means is that the new force is, the new gravitational force between the 2 objects is 8/9 of what the original gravitational force between the 2 objects was. That means that answer D is our answer here.